science department in the world. We have been celebrating this with a number of distinguished speakers this year, and we're concluding with a special event on April 5th, to which you are all invited. Information is available through the department webpage. We wanted to reach out to some particularly noteworthy members of the community who contributed a great deal to computer science over the years. And so we're very pleased today's distinguished speaker. Professor Barbara Liskov has the distinction of being one of the first, well, we believe at least one of the first 10, if not one of the first 5 or 6, PhDs ever awarded in the field. Receiving her PhD from Stanford quite some years ago. And I'm not going to put an exact number on it, you can mention it if you wish. And over the years has contributed a great deal to the theory of programming languages and abstraction with her work at MIT. Notable among this, the development of the CLU programming language, the Argus, fault-tolerant distributed processing system, and just as a benchmark here, the work she was doing in Argus is where I first met her as a new graduate student. So she's been contributing quite a few years to the field. But following that, the Thor system is one that's notable, a number of other things that have been developed. And along the way, she's picked up numerous honors in the field, Fellow of the ACM, John von Neumann Medal, and then she's the 2008 recipient of the ACM Turing Award, which is really the highest distinction in the field for her work in object-oriented programming and abstraction. She's currently working in Byzantine methods, and she'll be talking to us today about the power of abstraction. After the talk, there'll be a short reception. So please join me in welcoming Professor Barbara Liskov.
Thanks very much for that lovely introduction, and I'm delighted to be here today. As Jean mentioned, I got the Turing Award actually in 2009, which oddly enough is called the 2008 Turing Award. And at that time, I had been doing primarily work in distributed systems for a number of years. And so when I got the award, one of the things that caused me to do was to go back and think about the work that I had done that was the primary reason why I got the award. And actually, that's what I'm going to talk to you about today. So the problem that I was working on was the software complexity problem. And we all know that software is complicated and hard to build. Systems tend to be very big. They do complicated things. And to make things worse, they might be distributed or concurrent, which makes the reasoning about them harder. And a major theme of research in computer science has been how to keep this complexity under control. Oops. All right. You know, one of the streams of research in addressing complexity has been simply the invention of algorithms, data structures, protocols, techniques that help us to understand how to build our systems. And we've made tremendous progress in this. So nowadays, if you have to do search, you know that you may want to use a hash table or a B-tree, and you can go to your library and actually pull off the shelf some code that does that for you. This was definitely not true at the time I started this work. However, useful as this stuff is, it's only a tool. And before you can use it, you have to design your system and figure out how the whole thing works together in the first place. And that has been the topic of work in programming methodology. And as programming methodology has led us to understand certain things that are useful in the program development process, some of that work has migrated into programming languages. And that's what I'm going to be talking about today. So I'm going to first of all talk about programming methodology as it developed, as that field existed at the time I started this work and what happened next. And then I'll talk a little bit about how this has affected work in programming languages, and I'll end up with some remarks about programming languages today. So I started work in this area in 1970. So I got my PhD at Stanford in 1968. I actually did my thesis in artificial intelligence. I knew when I was working on my thesis that I wanted to change fields to the computer systems field. I decided to delay this change until after I got my PhD, since it was, you know, the main point of being in a PhD program is to finish up and go out and do something useful with what you learned. So as soon as I finished my PhD, I went to work at the MITRE Corporation, which is a company that does work primarily for the government. So the government puts out a request for proposals. MITRE might propose something to work on, and they get these grants. And I went to MITRE as a researcher, and the first project I worked on had to do with work in architecture and machine and operating systems. But around about 1970, when I finished that first project, I was asked to look into the crisis. So the software crisis, and this was a term that was used at the time, what this was an understanding that we actually did not know how to build the software systems that we wanted to build. And there were many stories through the 70s and 80s, even into the 90s, of catastrophes where millions of dollars and hundreds of man-years were spent on building some software which ultimately had to be tossed out because it simply didn't do what it was supposed to do. And the government was very worried about this problem because they had things in mind, and they wondered, what can we do to control the software development process so that in the end, we end up with programs that do what they're supposed to do. So this was the project that I was asked to look into. And this got me into the field of programming methodology, and I'm going to tell you about some of the papers that existed in that field at the time that I started working on it. But I just want to point out before I get started that programming methodology is actually about two topics. They're related, but they're not exactly the same. The first is, how do you do design? How do you design programs so that you end up with an effective structure at the end? And the other one is, what does the structure of programs be like anyway? Okay, so I'm going to tell you about the papers that I looked at. Not all of the papers, but some of them. I went back and read them when I got my Turing Award. They're really good papers, and I recommend to the students here that you read them. It's good to know what happened in the past, and these are very valuable papers. They also show you a lot about what was going on at the time. So the first paper I want to mention is a paper by Edgar Dijkstra, a go-to statement considered harmful. This actually wasn't even a paper, it was just a letter to the communications of the ACM. It was extremely controversial. And this is surprising from today's perspective because go-tos are gone, But in those days, the programming languages that people typically used had go-to statements, and so it was a different world back then. Now, the paper was controversial for a number of reasons. One of them was that people simply were insulted. They said, we use go-tos, but we write very nice programs. Saying that go-tos lead to bad programs, that's insulting to us. And they were right, because you can build a good program in any lousy programming language, provided you apply sufficient discipline to the way you use the language so that you avoid the traps that it might lead you into. On the other hand, there were many programs available at that time that people referred to as what they meant was that they were full of go-to statements, so the control structure was branching all over the place, and it was very hard to make sense out of them. Dijkstra's argument is actually a very interesting one. It was interesting at the time. It's actually very true. And what he said was, the reason we want to avoid go-to statements is because programs are hard to reason about. He said, when you reason about a program, you're looking at the text, which is static. But what you're thinking about is the execution of that text, which is dynamic. And since, in fact, it's hard to reason about programs, which in fact was also a statement that people didn't necessarily believe at the time, it's a good idea to keep the dynamic and the static as close together as possible. And this is relatively easy to do if you use well-structured control structures, like ifs and whiles and procedure calls. But it's arbitrarily difficult to do if you use go-tos. And an analogy to think about this argument is debugging. So if you're at a particular point in your program, there's a program error, and you're trying to figure out what the problem is. In order to figure that out, you have to understand how you got to where you are. If your program is well structured, it's relatively easy to figure this out. If it's got go-tos in it, it can be really, really difficult. Okay. One more point about Dijkstra is another reason why people were dismayed by it was that they were actually worried about whether you could program effectively without. Because at that time, programming as they were used, also they didn't necessarily have the control structures that we're with today. They didn't have exception mechanisms, they didn't have case statements, and in the absence of these mechanisms, go-tos are quite useful. Okay, the second paper I want to talk about is a paper by Nicholas Weert, Program Development by Software Refinement. This is a very early paper on top-down software development. And in it, Nicholas talks about the 8 queens problem. That's the example he uses. He says, well, what you want to do when you develop a design is you want to make one design decision at a time. And the example he used, he said, well, the design I'm going to make is I'm going to work on this column-wise. So at any stage in the design, I have a solution that works on n columns, and then I'll try to advance it to the n plus first problem. I'll try to find a place to put the queen on the n plus first column that satisfies the constraint. And if it works, I can go forward, and if it doesn't work, I'll have to backtrack. So that was his design decision. Now his idea was that you make this single design decision, and then you write it down as an abstract program, by which he meant just a bunch of comments. And then you reason about those comments and convince yourself that if you could implement them, they would be a solution to the problem. And then he said, okay, and then the hard part is, well, okay, what do I do next? And there he said, well, you select some of them and make another design decision and refine them further. Now, we know today that design is not entirely top-down. Sometimes you get through a design, you get to a particular point, you simply can't go forward, you have to backtrack in the design. But design has to be fundamentally top-down. It doesn't work to work from the bottom up, to say, what can I implement, and hope that you'll end up implementing the thing you're looking for. You have to keep your eyes on those requirements, let them force the design. Otherwise, you're not going to end up with a program that does what it's supposed to do. This is the third paper I want to talk about. This is a famous paper by David Parnas. David actually wrote 2 papers on this topic at about the same time. And in this paper, he says, programs consist of modules. He said, but tellingly, I don't have any idea what modules are. They're just the blocks. They're just pieces of code. Whatever they are, though, he said, the connections between the modules are the assumptions that the modules make about each other. So what he's saying here is, for this idea of modularity to work, we have to have some notion of the connections between the modules. And these connections have to be complete. They have to capture all the interactions that the modules make. Okay. So I want to stop for a minute and talk about modularity, which is in some sense, the fundamental thing we do when we build programs. We come up with a design that has modules in it, and we end up with a program that's a collection of modules. So as David said, a program is a collection of modules. Now, in modern terminology, then we say every module has an interface, which it presents to the rest of the program. And this interface would be described by a specification. This is what Dave was getting at when he talked about the connections. The specification would have to describe all the connections that this module presented to the rest of the system. And then what's nice about this is we have a modular way of reasoning about the program, because we can say, well, what does it mean for the module to be correct? Its implementation is correct if it meets its specification. And what does it mean for the rest of the code? Well, we can reason about the rest of the code just using the specification and not thinking about the implementation. So what we've done with modularity is we've taken a huge program, we've broken up into modules, and we can work on these modules independently. We can understand them independently, we can reason about them independently, and that's a huge step forward. So that's where Dave was going with this idea. And an example is a sort routine, where the specification just says at the end A is in sorted order. But if you looked inside, you would see a complicated program that accomplished the sort. Okay. Now what I just told, and the benefits of modularity are, first of all, the local reasoning that I told you about, but also modifiability. If I need to re-implement a module, if the rest of the program uses it through the specification and the implementation satisfies the specification, then I can insert the new implementation and not have to worry about the impact on the rest of the system. And then a third benefit, and I think this was the main one that modularity was used for at the time, was independent development. If I can break my program into modules, then I can give module A to this program or module B to that program, and hopefully they'll put something together that works. Okay, I was giving you a modern perspective on modularity. That was not the situation in 1970. In 1970, there was only one module mechanism that people understood, and that was the procedure. And the procedure, though extremely useful, is not a sufficiently powerful modularity mechanism to capture the kinds of modules we want to use in programs. Furthermore, procedures weren't even used all that much. And I can't think of the word. Before I went to Stanford, I worked at Harvard for a year on a language translation program where my job was to maintain a program written in assembler that had a printout about this thick. Those were the days when they printed out programs. And that program used procedures, but they were just like little blips on the side. So you'd be running along straight line. All of a sudden there'd be a procedure call. It would return more straight line. There's no modularity in this program because the whole thing is just one huge linear sequence. And programs were like that at the time. There wasn't a useful form of modularity. So modularity wasn't even used very much. Mostly it was used because you could say, oh, I want that code over here and that code over here. They're sort of similar. I'll put them together. Then I could save some space. I can make a call there instead of having to put the code in line. And that led to complicated connections. So that was the situation at the time I was doing this work. Now what happened was, I read all these papers, I read a bunch of others that I haven't got time to talk about, and I realized that in my work on Venus, which was the work I did before I started working on programming methodology, I had actually invented a methodology. And what happened was Venus was an operating system. It was a very advanced project at the time when operating systems that supported multiple users were still in their infancy. And I was very worried about, could my small team of programmers actually produce the code for this operating system, which was going to be complicated, so that it worked correctly in a limited space of time. And so I decided to deviate from the way that programs used to be built back then. It used to be that the idea was you had this big space of global variables, and then you had a bunch of code, maybe even block structure, all communicated through those global variables. Actually, David was talking about, pointing out that, it's feature calls, but if there's these global variables, worry about all the go through them. And that was I understood that was a big source of problems. So I decided in the design that we would not have any global variables. Instead, I took the global variables and I said they're going to be all partitioned. Each set of global variables are going to belong to a particular partition. That partition have them sort of hidden, and it will provide a set of operations that can be used by the rest of the code to interact with it. So this was just something that I invented so that we could keep Venus under control. But as I was reading those papers, I realized that this was actually a module, a kind of module that was very useful. And so I wrote this paper that I showed you. Pardon me, I went the wrong way. And I don't think I can go backwards. I have a question. This mouse doesn't seem to go backwards. So, huh? Well, there's one button here which goes forward, so I'm afraid to touch it. And there's another button here. Oh, I see what you're saying. I can use the mouse to go up to previous. Okay, previous. Okay, I'm going to do previous one more time. Not the ideal interface for giving a talk. So I wrote this up in a paper that I wrote in actually in probably 1971. Okay, now it's 1972, and I actually been working at MITRE for 4 years. And I had written up a paper on Venus, my operating system that I developed earlier, and it was one of the prize papers at SOSP. And so I went and gave it at SOSP, and the person running my session at SOSP was a man who was a professor at MIT, and he invited me to apply for a faculty position. Now, what had happened was, when I got my PhD, nobody was interested in hiring me. That's why I went to MITRE. I had no faculty job offers at all. I actually had one, but it was not a good one. And the truth was, there were very few women in the field. Nobody wanted a woman. It was an old boys network. By 1972, Title IX had passed. And Title IX was mostly about fairness with respect to athletic facilities, but it also had implications for women in other fields. And some universities were now interested in hiring women, and MIT was actually really interested. Jerry Wiesner was the president, and he said, we're going to hire some women, and so the departments were out looking. So I was asked to apply. I got a job at MIT. And there I was in the fall of 1972. And this was a really good time for me to move from MITRE to a university, because I actually had found the thing I was passionate about. I was really interested in this question about program methodology. And I would no longer have been happy working at a place where the next RFP comes in and you have to change your topic. I knew I wanted to work on this. Okay, so here I am in MIT in the fall of 1972, and the problem that was in my mind that I was thinking about all the time was the question about how can you really use these ideas in practice? Because what I felt was, if you look at these papers, including my paper on partitions, which was actually in some sense more defined than most of these other papers as far as modularity was concerned, you would say, oh yeah, that's a very interesting idea. I can see how that's a good solution. But when you tried to pull that idea into your own context and use it in your own system, it was totally unclear what to do with it. And so I was trying to figure out how could this situation be made better. And sometime in the fall of 1972 or the spring of 1973, I all of a sudden had one of those magical moments we all hope to happen, the aha moment, where I could suddenly see that my partitions could be thought of as data abstractions, abstract data types. And you know, it's really clear, I'm going to have to go backwards again, previous, in retrospect, you know, because that partition is really an object. And it has a set of operations that can be used by others to interact with it. So what is obvious in retrospect, but it wasn't obvious at the time. It was one of those things that's kind of, the idea was kind of floating around, but nobody was quite able to, you know, grasp it. Okay, so I made that connection, and I could see it was really important because for two reasons. One was I had linked modularity to abstraction. Okay, abstraction is how we really do design. We sort of abstract, you know, we think about something abstract and we'll worry about the implementation later. And procedures weren't powerful enough, but now with data abstractions, we had a whole new way of abstracting, so that was really important. The other thing was, I've forgotten what it was, so we'll worry about that later. Okay, all right. So I had this great idea, connect partitions to data types. And I wanted to stop a minute and talk to the students in the audience about work. Okay, so I had this wonderful idea, you know, but I am not a person who works all the time. I actually come to work in the morning. I work until, you know, for my 8 hours or 9 hours, whatever it is, not a sort of a normal day. I go home at night, I don't work, okay? And yet, I've actually been able to be very productive. And I think that the reason is I work really hard when I'm at work, and then I rely on the power of the unconscious. Okay, and never underestimate the power of the unconscious. So, you know, if you're focusing on stuff during the, so what happens to me is I'm thinking during the day, I go home at night, I don't work. In the morning, as I'm driving in, I start thinking about what am I going to do today. And I often find that I've solved a problem that I couldn't solve the day before. So that downtime is really valuable. Of course, enough sleep is also very valuable. So, okay. So now it's the spring of 1973, and I just wanted to mention this meeting in Savannah. This was an ACM SIGPlan SIGOPS interface meeting. So SIGPlan is the special interest group on programming languages. SIGOPS is the special interest group on operating systems. Ostensibly, this was to talk about programming languages in which to implement operating systems, which is a really boring topic. Okay, or not a very good topic to work on. And the reason is, you know, you can count on the fingers of one or two hands how many operating systems there are. You know, whereas there's thousands, hundreds of thousands of applications. So you really want to work on programming languages to support development of applications. However, in truth, the people at this meeting were interested in program methodology. And I talked about my work on data abstraction. And I started to work with Steve Zillis, who was a graduate student at MIT, also an employee of IBM, who had some similar ideas. Okay, so now Steve and I are moving from, okay, so the other reason why data abstraction was so important was because it was a familiar idea. Programmers already use data abstractions. Arrays are data abstractions. And so I felt that, you know, this was just a little bit different, and so it would be easy for programmers to grasp this. And so that was the second reason why I thought it was important. Okay, so Steve and I are moving into programming languages now. We're trying to make the move from this vague idea of data abstraction to an actual mechanism that could support it. And again, we read the literature, and I'm going to tell you a little bit about it. Of course, this is what you always do when you start a new field, right? You read the literature. Okay, so here's a paper on extensible languages. This was something that was popular in the late 60s and the 70s, where people were trying to say, it's not enough to have a language, you have to have ways of extending it, okay? And partly this came from a fact that people didn't believe in what they called universal programming languages. So they were dubious about whether you could have a language in which you could write all code. Now again, this is one of these concerns that seems like, you know, where were they coming from? Because we know we have universal programming languages. You know, Java is a universal language, C is a language, and so forth and so on. We use universal languages all the time. So this was a concern at the time because people were worried about the power they're going to lose from moving from machine language up to higher level languages. It's not a concern anymore. Although, frankly, when you're building a program in Java, you might have to use C a bit to get the kind of performance you need. Okay, so extensible language was a field where people were talking about how to extend your universal language. And we were looking for places where people had thought about data abstraction. This paper by Steve Schumann and Pierre Girand talked about two different kinds of extensions. The first was syntactic, where the idea was if I use factorial in my program a lot, why can't I use the factorial sign to call the function rather than having to call the factorial routine? This is a truly atrocious idea. Okay, syntactic extensions are a very bad idea, and the reason they're a very bad idea is because reading programs is much more important than writing them. Techniques that make it faster to write are not important. What matters is a program's going to be read many times by the person who wrote it and many, many, many times by somebody who didn't write it, and at least you want the syntax to rely on. You don't want to have some sort of mystery about what those symbols mean. Okay, they also talked in this paper about something more semantics, and Bob Balzer in this paper, Dataless Programming, explained a system in which every data type had a few operations. There was an insert, a remove, a lookup, and a modify. So they were thinking of data types as being collections. And that is a step along the way to abstract data types, except there was no encapsulation. So nothing was hidden about the way stuff was represented. And of course, data types differ a lot, and they don't just have 4 operations. This is a paper on Simula 67. So Simula 67 is a very important language. It was a precursor to Smalltalk, which was a precursor of the object-oriented stream of programming languages. And this is a paper by Ole Johan Dahl and Tony Hoare. Describes Simula 67 as it existed at the time. Steve and I looked at this paper. It has in it classes and subclasses and inheritance. It doesn't have any encapsulation. And so it wasn't getting at this idea of a module, having a closed interface with hidden stuff inside. And we decided that that was very important, and also we felt this whole inheritance thing was a huge distraction from what we were trying to do, so we did not follow the mechanisms in Simula 67. This is a paper by Jim Morris, Protection in Programming Languages, and Jim was interested in the question of modularity and what are the rules that have to be followed in order for modularity to work, and in particular, modifiability and separate reasoning. Okay, and so he said the rules are the code outside the module cannot modify the variables that are inside the module. That's necessary for reasoning because if code outside could modify, how could you possibly reason locally about this code? He said they shouldn't even look at that stuff, and that's important for modifiability because if the code outside can see the variables, then you can't rip this module out, replace it with another one, unless you preserve that as part of the interface. So I thought that was a very important paper because that was the first time these rules were kind of laid out in black and white. Then Jim said, I have no idea how to support this in a programming language. Here's an idea, and he basically described something like encryption. He had mechanisms seal and unseal. That's like encrypt and decrypt. So the idea is if the objects go out encrypted, then the code on the outside can't possibly muck around with them, without causing the program to break. So, we could see this was a kind of a solution to where we wanted to go, but if you had to implement it this way, nobody would ever have used it. Okay, so Steve and I worked on this problem, and my recollection of the summer of 1973 in Cambridge, Massachusetts was it was sunny all the time, because Steve and I used to meet for lunch outside in a lovely courtyard that was available at that time. Clearly, it wasn't sunny every day in Cambridge, Massachusetts, where it rains a lot. This just shows you something about the unreliability of memory. But at any rate, we met every day to talk about our ideas. Then we would separate, get together again the next day. And by the end of that summer, we had written a paper describing our ideas about data abstraction. And what that paper said was an abstract data type has a set of operations and a set of objects, and the important rule was the operations provide the only way to use the objects. It also contained a sketch of a programming language. Okay, so that's in some sense the methodology part. I took the methodology, I then clothed it in a programming language. This was really just a sketch. And so the obvious next step was then to push that into a real programming language because it's a long way from a sketch to a real programming language. And so that was the next step. And now it's the fall of 1973. And at that time, 3 first-year graduate students came in to work with me. And these three students, Russ, Craig, and Alan, together with myself, were the main designers of the CLU programming language. And what I'm going to do now is tell you a little bit about CLU. Okay, by the way, this is a picture of me in 1974, I think. I would have liked to have shown you pictures of the crew, but I don't have pictures from back in that time. And the person talking to me is Jack Dennis, who's a well-known person in the architecture field. All right, so going from that paper to a full-fledged programming language was the obvious next step. But I actually had a bunch of reasons why I thought it was very important to do this work in the context of a programming language. The first one was communicating to programmers. I believe that programmers think in terms of programming languages. We are naturally interested in implementing things. The languages that we have available to us color the way we think about the construction process. So by getting these ideas into a programming language, I felt I would make them much more available to programmers to build their programs. A second benefit of doing a language is you can tell whether abstract data types work in practice. I mean, this is obvious today, but it wasn't obvious then. And the idea was, people are going to have to write code, and they're going to have to use my language with abstract data types in it. If it turns out they can't express the things that they want to express, I'm going to find it out because it'll be very obvious. The third point was getting a precise definition. So, a programming language is a mathematical object. Of course, its description is typically not formal or mathematical because it's described in a reference manual. And there were many funny stories about programming languages at the time where the programming reference manual would be written, it would be ambiguous. Somebody would come along and build the first compiler, they would resolve the ambiguities without even really knowing they were doing it, and provide you with a working compiler. Then the second compiler comes along, and the ambiguities were interpreted differently, and so then in the end there was an argument about what is the meaning of the language really. Nevertheless, we tried very hard in the design of CLU to be very precise. It's a lot more precise than a paper that waves its hands and says, here's a vague idea, let's put it together. And I really believe the reason those papers were hard to follow was because they were so imprecise. And then the fourth point is reasonable performance. Performance is overstated in the programming, in the computer science community. You want your programs to be fast enough. They don't have to be as fast as possible. Nevertheless, if you had a mechanism and it turned out the programs were really slow, then nobody would be willing to use it. Okay, so I'm going to tell you a little bit about CLU, and I'm going to skip that slide. I just want to focus on the abstraction mechanisms. And in a way, these mechanisms are interesting because these are the issues that every programming language design faces, even today, because these are the mechanisms that language has to support. So I'm going to tell you about the various mechanisms, clusters for implementing. Rather than telling you that, I'll show you. Okay. So the first mechanism I want to tell you is clusters. So the fundamental problem you have to face up into in modern languages is there has to be some mechanism for implementing data abstractions. And in CLU, this was what we call the cluster. In fact, CLU, CLU, is the first three letters of cluster. And I'm just showing you a sketch of a cluster here. And the important point to notice is that in the top line, I'm listing the operations. And this was our way of making a point about the fact that a data type has operations, and the operations are the things you use to interact with the objects. See, and down here I'm showing you how you would use a cluster. See, here I'm calling the create operation of the int set. And this is interesting because it shows you our position on data types. We thought of the operations as belonging to the type, as opposed to, say, Java or C# where they think about the operations as belonging to the object. We actually spent a long time in the design trying to figure out which way we wanted to go, and we decided in the end that we wanted to support binary operations. So if you want to add two matrices, it's nice when you're inside to know that you have the same representation. But I think in retrospect it would have been better to go the other direction, mainly because of the syntactic overhead with having to use that $sign. Okay, now we knew even in the paper that Steve and I wrote that we didn't want to be able to implement just one type. We wanted to be able to implement whole families of types. So you don't want to have to implement int set, and then a minute later you have to implement string set, and then later on you have to, and so forth and so on. Instead, you want to implement sets, and you want to allow a value provided for the parameter at the time the set is used. And that's what I'm showing you on this slide. And at the bottom, you can see the syntax that we use for creating a set. when you created a set, then you provided a value for that parameter. So in this case, I'm creating a set of integers. Now, there was a problem with polymorphism, and it took us a long time to figure out what to do with this. The problem is that not every type makes sense as a parameter. So in the case of sets, you need an equality relation. And some types don't have that. So if you had a type that didn't have an equality relation, you wouldn't make sense to parameterize set with that. A more sort of compelling example is if I had a sorted set, then the type parameter must have some sort of sort, some sort of less than operation. And so if the type didn't have it, it wouldn't make sense to provide it as an actual. And it took us a while to figure out what to do about this because we wanted to do it with compile time checking, not with any sort of runtime mechanism. And this is our solution. We came out with a mechanism we referred to as a where clause. And the header of a parameterized module would have a where clause associated with listing the constraints on the actual parameter. So here we're saying T has to have an equal method which is a procedure taking in 2 T's and returning a Boolean. And then if you go back to the, oops, excuse me, I gotta do this again. Okay, so if I go back to the previous slide, what you can see now that once I have that where clause, the compiler can check when I instantiate whether the actual type has the operations that I require. Okay. Okay, I want to tell you a story about iterators. So I was very careful in the design of CLU not to go off in directions that I thought were not really focused on the question of what are data abstractions. So for example, early on in the project, I decided we're not looking at concurrency, although some people involved in the discussions wanted to do that because I felt it would be a big distraction. That was a really good decision because, as you know, managing concurrency is still a big problem today. We still don't really understand what to do about that. So I was very, focused on what we were doing, and then I got to this problem. Okay, we wondered, how do you express the program that iterates over a collection? If you gather stuff into a collection, and many data types are collections, then that's because you want to do something with those elements. You want to print them, you want to add them, and so forth. And so how do you express the program that does this? And we knew that we could do it without any extra mechanism. One way you can do it is you can go through the collection removing one element after another. That way you'll be able to process each element. But that's pretty inconvenient if you want to use the collection for another purpose, which you often do. Another thing you could do is complicate the abstraction. I could take my set and turn it into an index set, and then I could use the index to iterate over the elements of the set. But that was in some sense even worse than the destroy solution because you want to allow programmers to design the simplest possible abstractions, and having a lack of a mechanism in your programming language that forces them to do something more complicated, and this is the solution they would choose because you don't really want to destroy the collection, that's really a bad idea from a methodology point of view. So that was the situation in, I think, the summer of 1975 when I took my team of 3 graduate students and we went to visit Bill Wolf and Mary Shaw at CMU, where they were working on the Alphard language. This was the one other language project that was investigating how do you put data abstraction into a programming language. And they told us about generators, which were something they were putting into Alphard. And generators are like Java iterators. It's really unfortunate that the terminology has changed, okay? But in other words, they were additional objects. They had a create method, they had a next method, they had a are we done method, and so forth. And you can use these to iterate. It was clear to us that you could. It's just that we thought it was a very inelegant solution. And so on the airplane coming home from CMU, my student Russ Atkinson invented the idea of iterators. And iterators are like C# generators. Okay, this is just an example. So what's an iterator? An iterator is like a procedure, except that rather than just returning, it yields a bunch of elements, and then finally it returns. It's called in a for loop, and so you call it in the for loop, and each time it yields an element, you run the for loop body, and then go back into the iterator, and when the iterator is finished, then the for loop is over. That's a very simple idea. It's a 90% solution. So generators are more powerful because with generators you could walk over 2 trees and check to see that they have the same fringe. I can't do that with iterators. They are naturally nested. But we decided in this case that a nice simple 90% solution was better than a more complicated 100% solution, because after all, you can always use generators just by building them on the side for the cases where this is not going to be sufficient. And a final point is we had a very nice implementation technique. What the compiler did was it took the body of the for loop, turned it into a procedure, passed it as an argument to the iterator, and so every time the iterator yielded, it was just a call on the for loop body, and when the iterator returned, the whole thing was finished. And one final point about iterators, the reason they're much better than generators, what we call generators, is because the state of the iteration is sitting there in the program variables. And so when you go back in, you pick up right where you left off without having to build a whole bunch of data structures on the side to keep track of the state. Okay, that's pretty much what I'm going to talk about. CLU also had exception handling. And I think, exception handling is very important, and it's not being done very well in modern programming languages. And what you really want with exception handling is you want to focus on a methodology that says you write very strong specifications, where ideally the precondition for every procedure is true. And if it can't be true, it's something very weak. But as soon as you do that, you run into the problem that not every possible input can lead to the same output. Like, for example, you want to be able to read from a file, and you don't want to require that the file be non-empty when you read. But of course, you can't return a character if the file's empty. So you have to have different things. And exceptions are a very nice way of handling that. And the other point is, in CLU, procedures and iterators were first class. OK, so that was CLU. So now it's about 1968, 1970. I don't really remember when. And I was kind of looking around, figuring out what to do next. And I noticed the internet. So the internet existed in the 1970s, and I was using it for email and remote login, file transfer. But there was a dream about maybe we could build programs that ran on the internet, where they had pieces running on different computers. And I thought, wow, that's a really interesting problem. And so I jumped into distributed computing. And the alternative I could have done was to work more on CLU. I could have developed and maybe turned it into a commercial product. I think I made the right decision, but it's always been sort of a question. Anyway, I'm not going to talk about my work in distributed computing, which is where I've spent the bulk of my career since then, although I retain a very deep interest in programming methodology. And what I'm going to do in the rest of this talk is just tell you about one thing that I did after CLU, and that is what I say from CLU to object-oriented programming. Excuse me. Okay, so what happened was in 1986 or in 87, I think it was 86, I was asked to give the keynote at UPSLA. And UPSLA is the main conference in object-oriented programming languages. And at that point, I decided, well, this is a good chance for me to cut up to speed on what's going on in the object-oriented programming arena. That work had been going on completely independently from CLU. So I was working in the 1970s on CLU, and Smalltalk was also being developed and its follows-on, and they were sort of totally oblivious to one another. So in the 1980s, I decided this was a good time to find out what was going on. And so Smalltalk existed and some follow-ons as well. And Smalltalk provided inheritance, as you know. And I discovered when I started to read the papers that inheritance was used for two purposes. One is implementation inheritance, where you build the subclass by modifying a little bit, extending a little bit the superclass. But the other one was type hierarchy. And I was really interested in type hierarchy. And it was clear from reading the papers that people didn't understand it at all. Okay, did I go to the next one? It wasn't well understood. So I remember reading a paper that said that stacks and queues are each a subtype of one another. And I was certain this couldn't be true, because if I write a program that expects a stack and I get a queue, it may not behave the way I expect, because I might expect stack-like behavior and I'm getting queue-like behavior. And so this led me to come up with what has come to be called the Liskov substitution principle. I described this in my keynote at UPSLA and later wrote a little paper about it. And what I said in this paper was, what I said at the talk was, objects of subtypes should behave like those of supertypes if used via supertype methods. So basically what I was saying is, it's all common sense. I write a program, it expects an object of a particular type. It better behave like that type, even if in fact it really belongs to a subtype. I'm only going to use it through the methods that I know about, so I don't require complete, equivalence, I only required that it behave like it through the supertype methods. So that was the Liskov substitution principle. Of course, I didn't invent that name. Okay, what happened was, in about sometime in the 90s, I got an email from somebody saying, can you tell me if this is a correct interpretation of the Liskov substitution principle? And that's when I discovered that it had a name, and that not only that, but there was a large group of people talking about what it actually meant. And I worked later with Jeanette Wing to firm up and give a precise definition. Okay, so I'm just about done. So I got the Turing Award in 2009, and when I got it, my husband was online every day looking at the chatter on the internet. And one day he found this marvelous quote. It said, "What did she get the award for? Everybody knows this anyway." Okay, now this was not intended as a compliment, I'm sure. But in a way it was a huge compliment, because the truth was, when I did the work, nobody understood it. And today, everybody understands it. And that's really a marvelous thing. Okay, so I'm just going to conclude with a couple of remarks about programming languages. So one of the things that happened also as a result of getting the Turing Award is I started thinking about programming languages again, which I really had not been thinking about for the last 25 years. And I just want to end up with a problem that I wish we could figure out a solution for. Today, we have languages for experts. You know, there's Java, there's C#, there's C++, and so forth. And these are very valuable languages for building big, complicated systems, and they have very nice modularity mechanisms in them. But they're very complicated. And so what's happening when we teach programming is we're moving away from using those languages. Instead, we're using much simpler languages like Python or Ruby. And to take Python in particular, if you look at Python and you see what's happening in introductory course, it's really very nice. You know, you can write a little simple procedure. In some sense, the complexity of what you have to write is equivalent to, you know, how complicated the task is. The problem is, when you get a little bit more advanced, you discover that it doesn't have any encapsulation. Okay, so it threw out the fundamental principle of modular program construction along the way. And that's really unfortunate. Okay, so my question is, couldn't we have both? It would really be good if we could start programmers programming in a language that didn't do the wrong thing when you got more complicated. Because one of the unfortunate truths about our field is that people take that language they first learned and they start to use it to develop big systems. And you know, one of the things that happens is you start off with a simple version of your big system and everything's working just fine, and then it gets, you know, if it really works, then all of a sudden you've got 100 programmers working on it, and it's getting bigger and bigger and bigger, and things that were okay to do when it was small are no longer okay. So that's my final slide. Wouldn't it be nice to have a programming language that works for both novices and experts? And then what I put on the slide is just a few things about what I think. This is not an easy job to design this language. And so I just mentioned a few things. You want powerful abstraction mechanisms. Modularity and encapsulation are critical. Readability matters more than writability, but you cannot ignore writability. You always have this trade-off between ease of use and expressive power. And then what I have at the end is state matters. So there's a field in programming languages where people would like to think state doesn't matter. And I'm thinking here about the functional language community. But the truth is most of the programs we write are really focused on the management of state. And so although it's very nice to support a programming style where you don't modify data if you can avoid it, you know, if you don't need to, it's still important to have the other kind of data, also other kinds of modifications happening. And that is, the other challenge I have on the slide is the massively parallel computers. You know, I think this is a challenge of our time. How do we write programs that really run well on these machines? Okay, and that's the end.